We've done two videos about inferential statistics, hypothesis testing and confidence intervals. Both were trying to use a sample to say something probabilistically about the general population. We approached these by randomizing situations. However, as I said, there is a wealth of probability theory in mathematics that can just provide the required probability numbers for us, instead of having to run these simulations. I want to move in that direction, and this video is the first step, talking about the normal distribution and z-scores. Let me talk about the term distribution. This word is going to do a lot of heavy lifting in this section, so it is important to make sure it is very clear. A distribution is the shape or arrangement of some data. We first talked about this with histograms, one numeric variable in a data set put into bins and displayed with counts for each bin. This gave us a visualization of the data, a shape, a distribution. Here's the data that was used in Learning Outcome 6 about interest rates, showing a unimodal distribution with a right tail. We've already mentioned in passing the shape of a normal distribution. This is the bell curve, a unimodal, symmetric distribution. This histogram shows a roughly normal distribution shape. In this video, I want to really understand the normal distribution mathematically so that we can use it going forward. In mathematics, the normal distribution is a function. The probability theory of the normal distribution is all about understanding this function. For now, I just want you to recognize it. It is an exponential function with the special number e as its base. The exponent has a negative x squared with some constants involved, and there also is a constant in front, which has a denominator involving the square root of pi. It's a very strange expression, but it turns out to give exactly this shape if you graph the function. It is the bell curve. The normal distribution is entirely determined by two things, its mean and its standard deviation. The mean is at the top of the bell and is represented by the Greek letter mu. The standard deviation is a measure of how wide the bell curve is, and it is represented by the Greek letter sigma. These mu and sigma give the constants in the function, mu in this numerator, and sigma squared in these two denominators. Knowing both these numbers entirely determines the function. This means that there are many normal distributions with various means and standard deviations. Here are three. This tall one has a mean of 0 and a standard deviation of 1, which disappears in the expression of the function. The second distribution has a mean of 4 and a standard deviation of 3 and is more spread out than the previous. Finally, the third one has a mean of -3 and a standard deviation of 5, even more spread out. The point here is just that the mean and the standard deviation entirely describe a normal distribution, and therefore there are a variety of these to discover. All right, that's the normal distribution. Let me move on to z-scores. For normal distributions, a z-score is a way of measuring where one particular data point falls in relation to the distribution. It is calculated this way: the data point value x minus the mean divided by the standard deviation. That's the calculation, but what does it mean? Here is a normal distribution with mean 15 and standard deviation 6. Let me look at the value of z of 18. This calculates to 0.5. The data point 18 has a z-score of 0.5. Notice the standard deviation is 6, but the data point is exactly 3 units away from the mean. This is not a coincidence. A z-score counts how many standard deviations a data point is away from the mean, with positive above the mean and negative below the mean. It is a very convenient measure of how far out a data point is with respect to a normal distribution. Since almost all of the data for a normal distribution is within 3 standard deviations, typical values of z-scores range from -3 to 3, and only very extreme outliers would need larger z-scores. Now let me connect this to another definition from a previous video, percentiles. For a data point in a distribution, its percentile is the percentage of how many other data points are below it. Here is the same normal distribution with 18 having a z-score of 0.5. There is a way to go from z-scores to percentiles. For our purposes, that way will just be reference from a table, and that table is included on the Moodle page for your reference. The table says that z equals 0.5 gives a percentile of 0.691, or 69.1%. That means that 69.1% of the data is below this, and therefore 30.9% of the data is above it. Finally, there is one last lovely interpretation here: the area under the curve. This area is exactly 69.1% of the total area on the curve, and this area is exactly 30.1%. Geometrically, the area to the left of any data point is its percentile, which is pretty great. That's what we're going to need for z-scores to set up the class activity. But I'm not entirely done for this video yet. There is one more important topic to cover today. Let me go back to the idea of distributions. This was the sample distribution I showed earlier. It is the shape of one variable from one sample. Now go back to learning outcome 11, where we did a simulation for hypothesis testing. Assuming the null hypothesis, we generated difference in heights between men and women by generating random samples, by shuffling the data. Each difference here, then, is the difference from a unique sample. 10 samples, 10 differences. These differences are also numeric data, so I can make a histogram of those differences. There are 10 samples, 2 in the first bar, 2 in the second, 2 in the third, and 4 in the last. This is also a distribution, but a different kind. This is a sampling distribution. Each count is one randomly generated sample, and the distribution shows what happens over many different randomly generated samples. And this is what we use in hypothesis testing to calculate a p-value. So I have several different distributions running around. A statistical study starts with a population parameter that it wants to investigate. Let's say that parameter is a proportion or a difference in proportions. There is a distribution for the whole population. This is the population distribution. But this is unknown, so we can't measure the whole population. Instead, we take a sample and get a sample statistic, which is like the parameter and hopefully represents it. In this case, the sample statistic is a proportion or difference in proportions. Then I've just defined the sampling distribution. This is the distribution of the statistics for many different samples. Either different samples that are measured, or like in learning outcome 11, different samples that are randomly generated. The sampling distribution was what we used to generate the p-value, even though we didn't call it a sampling distribution at the time. This is getting hectic, so let me be very careful. A sampling distribution is not the display of the cases in one sample. Instead, each sample generates a statistic, one number from each sample, and that produces a new kind of data set with one value for each sample, and the shape of this data set is called the sampling distribution. And this lets me state the big mathematical idea that pulls together both parts of this video. This is a fundamentally important result which makes much of the probability theory work. Say we are measuring a statistic which is a proportion or a difference in proportions. Assume that the observations in the sample are independent. That is, each measurement doesn't affect any other measurements. This will be usually true for well-designed studies, but it does need to be stated. Then also assume that the sample size is large enough, with, again, large enough to be worked out later. Then, if I generate many samples and calculate the statistic for each, I would get a sampling distribution, and the theorem says that the sampling distribution will be roughly a normal distribution. This is sort of crazy. The population doesn't have to be normally distributed at all. I have no idea what the population data actually looks like. But if I take many samples and take the statistic from each samples and graph that data under these assumptions, I always get something that gets closer and closer to a normal distribution. This is a real mind twister, and if your head is spinning right now, that's all right. The real takeaway here is that this result, which is called the central limit theorem, is going to justify the use of the normal distribution for some of the next few videos. It is the big mathematical truth that makes it all work.